Okay, kids, we're back studying some more electricity and stuff about electric circuits. Now, I hope you watched the video. We're watching segment 6. So if you didn't watch the video first, pause this and watch the video first. So I assume everyone watched the video, and the video was about Ohm's law. And Ohm's law is a law that shows the relationship between the current that goes through a load, right? The current that goes through a load and the voltage drop that you get at the load. And it's a very straightforward relationship. If you take the voltage in volts and you divide it by the current in amps, you get the resistance of that uh, resistor or of that load. Now, a load can be a resistor, a load can be a motor, a load can be a light bulb, a load can be a speaker. Anything that takes electrical energy and converts it into another type of energy is a load. And the resistance of a load is in volts per ampere or ohms. Now, the symbol that they use for ohms is not O for ohms, right? Because then it would look like a zero. That'd be confusing. So they've decided to use the Greek letter omega. Looks like this. Omega is a volt per amp. All right, and I'll give you some questions to do on this very straightforward equation. Some of you may want to use a triangle if you want. I know some of you like triangles, right? Put the volt there, current there, and the resistance there. All right. So the next thing we want to study is when we have a series circuit. Series circuit meaning that there are loads arranged in series. What is their total or overall effect? What is their total resistance on the flow of current that leaves the source? How do we do that? How do we calculate that? Well, let's say that we have a resistor here. It would heat up if current goes through it, and it has a resistance of 5 ohms. Let's say we have a motor here, and it has a resistance R2, say 10 ohms. And let's say we have a light bulb here, and it has a resistance, and we're going to name that resistance R3 of 15 ohms. The total resistance on the flow of electrons from this source would be R total, T for total. And we calculate that by adding them. So 5 plus 10 plus 15 is 30 ohms. That would be the total resistance of this load arrangement. What if the loads are arranged in parallel? Look, I got a light bulb here with resistance R1 and a motor here with resistance R2 and a resistor heats up here with resistance R3. Each of them have their own branch. How are they going to affect the flow of electrons that come to and leave the source? How is that going to affect? What is their total resistance on the source? Well, you add it up differently. Remember RT, T is for total. So it's an inverse sum. So 1 over the total resistance, which is what we want to calculate, is equal to 1 over the first resistance plus 1 over the second resistance plus 1 over the third resistance. And if there were more, we would just keep on going on. So let's continue here. So we add them up. 1 over our total is equal to 1 over 15 ohms plus 1 over 5 ohms plus 1 over 10 ohms. Now, what you need to be really careful about here is 1 over 15 ohms does not equal 1 over 15th and then the ohm. Here the ohm is in the numerator. Here the ohm is in the denominator. The ohms are in the denominator here. Please be very careful about that. Well, what we got here are 3 fractions with 3 different denominators, so we're going to find a common denominator. So we multiply top and bottom here by 2, and we get 2 over 30 ohms. top and bottom here by 6, and we get 6 over 30 ohms. Top and bottom here by 3, and we get 3 over 30 ohms, which gives us 11 over 30 ohms. Notice the ohms is in the denominator. So that means 1 over the total resistance being the total effect of this arrangement of loads on the source, is equal to 11 over 30 ohms. Well, I flip this side of the equation. That means I got to flip the other side of the equation. And I get total resistance is equal to 30 ohms over 11. Then I divide the 30 by 11, and I get 2.73 ohms. So what's very interesting here is that the total resistance of these three loads on the source is 2.73 ohms. It's actually less than the 15 ohms you'd find here, the 5 ohms you'd find here, and the 10 ohms you'd find there. The resistance is less. And the reason the resistance is less is the electrons have 3 paths available to flow through. When there's 3 paths to flow through, the resistance is lower for flow. Same thing with water. If you allow water 3 different places to flow through, wherever it came from, wherever it started from, it would flow quite easily through that because there are so many paths. All right, the next part of today's lesson is called circuit analysis. And what is our goal here? Our goal is to calculate the current and voltage at loads when we are given the source voltage and the load resistances. Whoa, what does that mean? Well, let me show you in an example here. Here's a circuit, and we know in this circuit that the voltage at the source is 120 volts, so we've been told that. And we see here that this is a really different kind of circuit. It's a mixture of parallel section, and then before the parallel section, there's another load. So a load before other loads means series. So this is actually called a mixed series parallel circuit. It's a mixture of the two. It's got different sections, different arrangement of loads with each other. These two, the motor and the light bulb, are parallel to each other. But the resistor, something that would heat up, is before both of them. So the resistor is before the parallel arrangement. So the resistor is in series with the parallel arrangement. That's called a mixed series parallel circuit. What else do we know? Well, we know that the resistance of this resistor, R1, is 15 ohms. The resistance of the motor here, R2, is 5 ohms. We know that. We've been told that. And we know that the resistance of the light bulb is R3 and it's 10 ohms. Now remember our goal here. Our goal is to find the current that leaves through and it goes back into the source. S is for source, right? The voltage source. What's the current there? And what's the current and voltage drop at the resistor? What's the current and voltage drop at the motor? What's the current and voltage drop at the light bulb? And how are we going to solve all this? Well, we're going to solve the question. We're going to solve our goal. We're going to meet our goal by using Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law, and knowing how to add up resistances to find total resistance when they're in series and when they're in parallel. So basically what I'm saying to you is all this neat nifty stuff we've learned, we're now going to apply in circuit analysis questions. I hope you're excited. So let me show you how this works. And I'm going to use this method to show you. On this side of the purple line, the left side of the purple line, I'm going to show you steps that you can use in any circuit analysis question you're ever given. On the right of the purple line, I'm going to show you how I'm applying that step to this particular circuit. So here we go, steps. Step 1A, add loads in parallel to find an equivalent circuit. Now hold on, you haven't seen this word before, equivalent circuit. I'm going to show you that in a moment, so don't you fret. Okay, so one of the ways that we can find parallel total resistance is this other nifty way that some of you may like to do. If you want to find R total parallel, a neat way of doing it is simply multiply the two of them that are parallel in the numerator and divide by the two added together. So it's a little bit different than this one, right? R1 over R total is equal to 1 over R1 plus 1 over R2, right? Remember how I taught you that a few moments ago? This is an alternate way of doing it. You multiply the two of them together, then you add the two of them together in denominator. So let's see how that works for this one. R2 and R3. So here's R2 is 5 ohms. R3, right, is 10 ohms. So 5 times 10, and they're both ohms. So 5 ohms times 10 ohms. 5 times 10 gives me 50. Ohms times ohms gives me ohms squared. Now we're going to add R2, 5 ohms, and R3, 10 ohms. That's what we have in the denominator here. Well, 5 ohms plus 10 ohms is 15 ohms. Then you divide 50 by 15, you get 3.3. You divide ohms squared by ohms, and you get ohms. So this is kind of like a quick way of doing this one instead. Okay? Now, let's get back to this equivalent circuit. Let's get back to this equivalent circuit. What I'm going to do now is I'm going to redraw the circuit, but I'm going to combine those two parallel loads into an imaginary load called R total parallel. So here is the source, it stays the same. Here's the load from the resistor, R1, that doesn't change, but I'm constructing in my mind an equivalent load of 3.3 ohms that is going to replace that parallel section. So this right here, even though it doesn't exist in the real world, it's very much a mathematical construct, it is a good tool to use to solve this problem. So this is the equivalent circuit right here. It's got R1 in it, and it's got R total parallel of 3.3. So we move from there. Part B, add loads in series for an equivalent circuit. All right, well look at this circuit that it is now equivalent. These two are in series to each other. Even though this circuit doesn't really exist, it's a mathematical tool for solving, it's still very good. So now we have R1 right here, which is 15 ohms, plus the 3.3 ohms that is from adding the two in parallel, and we get 15 ohms plus 3.3 ohms gives me 18.3 ohms when these two are added together. All right. So we're now going to draw our final equivalent circuit. Here's the source, still 120 volts. And now we have our total. We've added up all the loads, and all the loads are mathematically represented by our total of 18.3 ohms. All right. Now, if there were other loads to add, that's what step C would be. Add remaining loads as needed for an equivalent circuit. So as you go through this, you're combining loads, and you're always redrawing a more and more and more simple circuit until eventually you end up with the one source and the one equivalent load. Now remember, this circuit here, it doesn't exist. It's just a mathematical construct that we're using to solve this. So we have now calculated total resistance. It's 18.3 ohms. What does that mean? It means that these three loads in this particular arrangement have 18.3 ohms worth of resistance acting on that source. That's what it means. And we've simplified it for our benefit to an imaginary circuit with just one ohm, which is with just one load with 18.3 ohms of resistance. There we have it. Step number 2, use the last equivalent circuit. So here's our last equivalent circuit. And Ohm's law to find the current that goes through the source, IS. So this is what we write. We're going to use Ohm's law. Voltage at the source is equal to the current at the source times the total resistance. I'm going to rearrange this. Okay? And it's going to be current through the source is equal to voltage at the source divided by total resistance. So it's 120 volts divided by 18.3 ohms gives me 6.6 amps. So wow, we've just solved one of our unknowns. We've just figured out that the current that leaves the source is 6.6 amps. 120 volts divided by 18.3 ohms is 6.6 amps. There you have it. Current at the source. But we got other stuff to figure out, and that's where the third step comes about. And the third step says apply Kirchhoff's voltage law and apply Kirchhoff's current law to the original circuit. You got to go back to the original, all right? To the original circuit to create voltage and current equations. So let's deal with Kirchhoff's current law first. Here we go. You've got the current that leaves the source, and then that current goes through the first resistance, the first resistor, the first load right there, okay? Well, the current that left here isn't split up anywhere. It's still going through here. It's still the same current. So the first equation we can write is current through the source is equal to current I1. And that's one of the equations here. Look, I1 is equal to I source. So therefore, I1 is 6.6 amps. Wow, look, we have just calculated what I1 is, 6.6 amps. Let's continue with Kirchhoff's current law. Here we go. So current IS leaves the source, goes through the first load, so I1 and IS are the same. Aha, gets to here. So IS splits into two branches here. IS, the current from the source, splits into two branches. So you got branch here with current I2, branch here with current I3. Let's make an equation out of that. Look, IS is equal to I2 plus I3. And then we put in 6.6 amps for IS because we know that. And then we have I2 and I3. Well, we got two unknowns in the equation. We can't solve it right now, but that's okay. We still have other work to do. We're just going to leave this aside for a little bit. Let's apply Kirchhoff's voltage law now. Let's apply Kirchhoff's voltage law. Here we go. So Kirchhoff's voltage law says whenever you've got some current leaving the source and it makes a complete path into the circuit and goes back to the source, whatever the source voltage was, it has to be used up on the loads that the current experiences. So we got voltage source here. Then we got the first load. So at the first load, we have R1, I1. You would have a voltage drop V1. Let's keep on following the path of the current. We run it here. This is the motor. The motor has a certain current through it, I2, a certain resistance to it, R2. It has a certain voltage drop, V2. And then the current goes back home. So that is our first Kirchhoff's voltage law equation. Look, Vs is equal to V1 plus V2. And we know Vs is equal to 120 volts. So 120 volts is equal to V1 plus V2. And we stop there. We got two unknowns in this equation, but that's okay. We got more work to do. let's keep applying Kirchhoff's voltage law. So there's another path here. Some of the current left the source, didn't go up the first branch, but went up the second branch and then back home. So we have voltage source here. We'd have a voltage drop at the first load, which would be V1. This current goes this way. Aha, the third load with a resistance R1 and a current, R3 and a current I3, well, it's going to have a voltage drop V3. V3 goes with R3 and I3. And then the current continues and it goes back home. So I can write an equation about that. Voltage source is equal to V1 plus V3 and nothing else. So let me write that down. Here's my next equation. Voltage source is equal to V1 plus V3. And I know that Vs is equal to 120 volts. So 120 volts is equal to V1 plus V3. And we leave it there because there's an equation but two unknowns. We can't move forward, but that's okay. We've got more work to do. What is the fourth and final step? Use Ohm's law, okay, at the loads to complete the Kirchhoff voltage law, Kirchhoff current law equations. So we're going to use Ohm's law where we can. Well, let's think about the first load. The first load. Do I know the current at the first load? Yes, it's 6.6 amps. Do I know the resistance there? Yes, it's 15 ohms. So I use Ohm's law. V1 is equal to I1 times R1. And I get that the first voltage is 99 volts. 99 volts. All right, that's the first thing we do. Then we take that 99 volts. Look at what I've drawn here. I've drawn the arrow here. I take that 99 volts. I put it into this equation for V1. I put it into this equation for V1. If I do that, now I have only one unknown in the equation. And that means I have 120 is equal to 99 plus V2. 120 volts is equal to 99 volts plus V3. It means both V2 and V3 are 21 volts. So look, I've just calculated that V2 equals V3 and it's 21 volts. Awesome. What's left to calculate? Well, kids, I still don't know I2 and I3, right? But maybe I can use Ohm's law, just like the fourth step tells me, to calculate that. So here's Ohm's law at the second load. V2 is equal to I2 times R2. I rearrange this equation. I get I2 is equal to V2 over R2. I know V2 is 21 volts. I just found that out. Divided by the 5 ohms, I get 4.2 amps. Going to do the same thing at I3. V3 is equal to I3 times R3. I rearrange it. I3 is equal to V3 all over R3. I get 21 volts because I just calculated V3 to be 21 volts. Divided by 10 and I get 2.1 amps. So look what I just did. I found I2 is 4.2 amps. I found out that I3 is 4.2 amps. Guess what, kids? We're done. So I'm going to give you some homework to do. I gave you some notes as well, and I gave you a bunch of other examples of circuit analysis to look at. All right, thank you very much, and have a great day.